Good evening and welcome back to Dr. Logic Awkwardly Does Logic. This is going to be the start of a little mini series of videos on correspondence results. And in particular, what we're going to look at is correspondences between the validity of particular modal formulas, many expressing kind of natural properties that we might want to see in our modal systems, and particular properties of the accessibility relation in our Kripke frames. So before I can actually start talking about what these results look like and how to prove them, I need to say something about frame properties. So that's what this video is about. When we first started talking about possible worlds, accessibility relations, we didn't really say much about what this accessibility was. We just said, oh, we're only interested in the relevant possible worlds without saying anything about how to determine relevance. Now, I'm still not going to say very much about that because relevance is something that comes from the outside. It's not something that logic is going to tell you. However, you can figure out what types of things might be relevant on the basis of what are the modal principles you want to have valid. So you can see how all of these bits are they're all kind of interlocking with each other. So we have to kind of reach in and grab one in order to get started with all of these kind of circularly related things. So the one I'm going to grab in and start with are frame properties. This is going to be fairly abstract, but once we start kind of moving on to the next bit of the circular, connection of concepts, you'll start to see examples of these frame properties and how to understand them. And trust me, it will be understandable. So what we want to do is take a look at different things that you can express just simply about how we are drawing these dot and arrow diagrams. So most of the time so far, we've been doing whatever we wanted without any concern about ensuring that we have frames of a particular kind. That changes now. So let me clear all of this. I'm just going to start off by giving you a bunch of definitions. So we have the property of reflexivity, which just says every world can see itself. So I'm going to express these relations both using predicate logic notation, but also by kind of drawing a representation of a little bit of what the frame looks like. Now, we also have irreflexivity, which says that no world can see itself. So every world is going to look like that. It's important to recognize that between reflexivity and irreflexivity, we have non-reflexivity. Non-reflexivity is just the negation of reflexivity. Since reflexivity is a universal claim, non-reflexivity is an existential. It is that there is at least one world that doesn't see itself. So you can see it's not the same thing as irreflexivity, which is where no world sees itself. So we've also got other useful frame properties that we will talk about. Seriality. That is when every world can see some other world. So it could be itself, it could be another world. So one thing that you can immediately see is that reflexivity implies seriality. If your flame is reflexive and every world can see itself, then every world can see some world. There's also the frame property of having no first point. So this is kind of the converse of seriality. This one says for every world, there's another world, and that world, so here, if that's X and this is Y, having no first point is going to be like this, because then as soon as we have this Y, we know that there is something that sees it and something that sees it and something that sees it, and so on to infinity. No first point is very useful if you are modeling time and you think that time is infinite into the past. You might not. Another very popular frame condition is transitivity. Transitivity says that if you've got every X, every Y, and every Z, and X sees Y, and Y sees Z, let me make sure I've got my parentheticals right. Then X also sees Z. So if we have something that looks like this, then we've also got an arrow from here to here. Another related notion is going to be symmetry. And that says that for any two pairs of worlds, if one sees one world, then the relation also goes back the other way. So if X sees Y, then Y sees X. Anti-symmetry, like irreflexivity, is where there is no symmetry anywhere. So again, there's a distinction between anti-symmetry and non-symmetry. Non-symmetry just says there's at least one pair of worlds where the first one sees the second, but the second doesn't see the first. Whereas anti-symmetry says that this is kind of the case across the way. So anti-symmetry is the property that we have when for every X and every Y, if X sees Y, then it's not the case that Y sees X. So it's forced that you can't have this symmetrical relation. Now, there are a number of other any relation that, whatever your favorite relation on kind of a binary, whatever your favorite property of binary relations you have, you can talk about it in the context of a Crick frame. So there's going to be things like the relation being a pre-order or a strict order or a weak order or any of these. If you don't know what these are, go ahead and look them up. You might find something interesting. If we use them going forward, we'll define them when we need them. I'm not going to write the definitions out now. You've also got notions of equivalence relations, which is any relation that is reflexive, transitive, and symmetric. So any relation that is all three of these, we also call an equivalence relation, which is not the same as the universal relation, which just says for every X and every Y, X sees Y. And I will later on show you a frame that discriminates between the universal relation and the equivalence relation. So it'll be a frame where we have the equivalence relation, but we don't have a universal relation. Other useful things that, again, when we need them, I will come back and define them explicitly, are things like density and linearity. And I should have prepared better and had both pages of my notes in front of me. There we go. Ooh, yes, trichotomy is another interesting one. So trichotomy is the relationship that says for every X, Y, and Z, if either X sees Y or Y sees X, or sorry, this isn't an if then. I didn't read the entire formula before I started writing it up. Trichotomy, please ignore that. Trichotomy is the relationship that says that for any two pairs, either they are identical or one sees the other or the other sees the first. And then we have convergence, which is also known as the diamond property, because as you can expect, we get a lovely diamond out of it. So convergence says, and here I'm just going to draw the diagram. If you have an X that sees a Y and an X that sees a Z, then we know that there's always going to be some world ahead of them where they converge. So every time that your path branches, it'll always come back together. And then finally, we have the notion of being that is supposed to be a C and an L, Euclidean. And the way you can remember what the Euclidean relationship is because it has to do with drawing triangles. Euclidean relation is the one where for every X, Y, and Z, if X sees Y and XCZ. I think I need one more parenthesis there. Then Y also sees Z. So it starts off the same as the convergence relation. So X sees Y and X sees Z, but then we just form the triangle by going like this. And because this talks about every X and every Y, we also know that the arrow goes the other direction. So there's a whole bunch of frame properties. And don't worry, as I said, whenever we come to the point where we're actually going to be using these, I will reiterate the definition. So you don't have to remember all of these. You just kind of need to know right now, these are the sorts of things that I'm interested in when I talk about frame properties. It's going to be things like this. So join me next time and we will start looking at actual correspondences between these properties and modal formulas. We'll start off with reflexivity. It's the easiest one. So join me then. And until then, take care. Goodbye.